Okay, so in this video, I'm going to show you how to simplify square roots using, I have two methods. So using one of the methods, which is prime factorization. So in the next video, I'm going to show you how to do it using a perfect square method. But for this, we're going to talk about prime factorization. So we already know how to find the square root of a number that is a perfect square. So what is a perfect square? So a number is a perfect square. So we think about a square and we think about 2 times 2. The area is 4. So 4 is the perfect square. So 9 is a perfect square because 3 times 3 is 9, right? So our perfect squares are going to be 1 squared is 1. 2 squared is 4. 3 squared is 9, and so on and so forth. 16, 25, 36, right? So we can take the square root of all these numbers. If I take the square root of 36, I know it's going to be 6. But here's what's important, is that it's going to be the positive 6, right? Not negative 6, because this is called the principal square root, meaning it is only the positive. Only positive. That is really, really important here because technically there are two numbers that when you square it, you get 36, and that's positive and negative 6. But we are only focusing on the positive because this radical here is the positive square root. So we are only working with positives here. So what is the prime factorization method? So this is for when you are factoring, or not factoring, I'm sorry, simplifying a square root that is not a perfect square. So for example, let's do the square root of 8. The square root of 8. 8 is not a perfect square, obviously, because look at our list of perfect squares. You go from 1 to 4 to 9. So the prime factorization method tells us that if we break 8 down, so we're going to take 8, which is our number. This is called a radicand. We're going to take the radicand, we're going to break it down, okay? And I know that this is an even number, so it's divisible by 2. So it's 2 times 4 is 8. Now, 2 is a prime number. Prime meaning that the only factors of it are 2 and itself. 1 and itself, right? But 4 is not, so I could break this down a little further into 2 and 2. So now I have 3 prime numbers. So what this tells me is that the square root of 8 is the same thing as me saying the square root of 2 times 2 times 2, right? 8 is 2 times 2 times 2. I can even test that out. 2 times 2 is 4. 4 times 2 is 8. True statement. So I took these three numbers, and I'll even keep the highlighting going, and I just wrote this out, okay? Now, this is where you have to pay attention more than ever. Okay, I'm going to break this out into pairs. So a lot of times I use this radical as a jail analogy, right? So these numbers want to get out of jail, right? Think Monopoly. They're trying to get out of jail. But if you're trying to escape jail, you want to escape jail with a partner, okay? And you want a partner that kind of is like-minded to you, right? So think about these twos trying to escape jail together because they're similar to each other, right? Because they think they have the same opinions of politics, whatever you want to think about, right? 2 and 2 want to get out of jail together. So these two numbers right here, so I'm going to rewrite this just for color sake, right? 2 times 2 times 2. These two numbers right here are going to get out of jail. They're going to escape jail together, okay? And they're going to escape jail as one, okay? They share an identity now. And so that 2, the double 2, became 1, 2 out of jail. And now who's left by his loner self? That 2 on the inside. Okay? And I'm actually going to put this in a color so you guys see what is actually staying on the inside. So again, these twos come, this is, if you really want to think about it mathematically, right? So 2 times 2 is 4. The square root of 4 is 2. This is really, let's use a different color. This is really saying the square root of 4, which is 2. Now, that is your final answer. 2, I'm going to rewrite it here so it is less colorful. 2 root 2. Actually, I'll rewrite it like this. So the square root of 8 is the same thing simplified as 2 root 2. Let's do another problem. So if I have the square root of 36. Oh, wait, that's a perfect square. That's not going to work. 45. Okay, let's do prime factorization. So 45, it's not an even number, so I know it's not divisible by 2, but it has a 5 at the end, so I know it is divisible by 5. So I'm going to do 5, and it's 5 times 9, which is 45. So which one of these is prime? If any, it's going to be 5. So 5 stays, and then we have to break down 9 more. 9 is 3 times 3. So I have 45 is the same thing as me saying the square root of, and I'm going to write them in order, 3 times 3 times 5. 3 times 3 times 5. I just took them from there. Now, which one of these are pairs? I can take out this double 3, and that double 3 is going to escape jail as a single 3, right? So there's that single 3, and then I have that 5 left over by his lonesome self. So the square root of 45 is the same thing as 3 root 5. And let's do one more problem. If I have the square root of 108. Now, 108 is not a perfect square, but it is even, so I could break it down using a 2. So I have 2 times 54. 2 is prime, so I leave it alone. 54 is not, so I can keep going. So this is another 2, because it's even, times 27. 2. Now, 27 is not even, but I know it's divisible by 3, so it's 3 times 9. That 3 sticks because it's prime. And then this becomes 3 and 3. So they are all prime numbers. So I can rewrite, and this is where this method gets a little bit tedious, is when you have a lot of prime factors. So I have 2 times 2, always write them in order, times 3 times 3 times 3. So now I'm going to take out not only a pair of 2s, but also a pair of 3s. So the 2s come out as a 2. The 3s come out as a 3, and they're going to be multiplied together because everything's being multiplied, right? So this is my 3, this is my 2, and then what's left by his or her or its lonesome self, that 3. So I have 2 times 3, which is 6, root 3, which is my final answer.